Imagine your mother calls your name. Ashok. The sound travels through the air, carrying a message. Or think about a phone ringing. The ringtone tells you someone is calling. In both cases, something is changing over time to deliver information. We call that a signal. A signal is anything that changes. Take a look at this patient in a hospital bed. That medical equipment is recording a heartbeat. Every single pulse is a constant flow of information, updating second by second. That heartbeat is a signal. Now look at this man examining a ticker tape at the New York Stock Exchange. The numbers are tracking prices ticking up and down. Mathematically, those changing stock prices are exactly the same type of data as the patient's heartbeat. They are both signals. Algorithms and the Fourier Transform analyze the mathematical translation of these events, the signal itself, rather than the physical music or the money. This diagram shows our baseline mathematical canvas. The independent variable is time, measured in seconds, and written as t. The signal itself is written as x of t, read as x of t. It represents how our signal changes as time marches forward from 0 toward infinity. In Python, you might generate this time axis using linspace. When we take that raw signal, x of t, and run it through a filter or a computer program, we get a result. That new processed output is written as y of t. Together, x of t and y of t form what we call the time domain. This is the mandatory starting state for any continuous signal. You have to map the data over time before a Fourier transform can begin its work. This diagram shows a smooth sine wave. We model this mathematically as x of t equals a sine omega t plus phi. The a stands for amplitude. It measures the physical strength or maximum height of the wave from 0. Next is f, or frequency, measured in hertz. It counts how fast the signal repeats every single second. The exact time it takes to complete just one of those cycles is the period, written as a capital T. Since period and frequency are opposites, t equals 1 divided by f. There is a second way to measure that speed. Instead of cycles per second, omega measures angular frequency. Think of one full cycle as a complete circle, which is 2 pi radians in geometry. Omega tells us the angle covered per second, so omega simply equals 2 pi times f. Finally, we have phi, which represents phase. Two signals can have the exact same amplitude and frequency, but start at different times. Phase measures that specific starting position, or offset. When mathematicians run a continuous Fourier series, their entire goal is to extract those exact variables, amplitude, frequency, angular frequency, and phase, from an incoming wave. These 4 anatomical variables provide the specific mathematical coordinates needed to describe how a continuous signal behaves at every moment in time. This diagram shows a smooth, continuous wave, x of t. Modern computers cannot store this infinite stream of continuous data. To process the signal, the computer has to scan it and measure one point at a time, leaving behind a series of discrete dots. We call this process sampling. The number of dots captured every second is the sampling frequency, written as fs. The time gap between each dot is the sampling period, ts. We have moved from a continuous timeline to a discrete digital environment. Actual stopwatch time is no longer our main focus. Instead, we use n, an integer sample number. We count the dots, 0, 1, 2, 3. The time interval between dots is delta t. Our notation changes too. The digital signal is now written with brackets, read as x of n. Let's test this. If a system samples data every 1 millisecond, what are the sampling frequency and the time interval? The frequency is 1000 hertz, and delta t is 0.001 seconds. Converting the continuous wave x of t into this discrete array of numbers, x of n, is a strict requirement. You must build this digital bridge before any algorithm, like the fast Fourier transform, can process the data. Listen to an orchestra. Dozens of instruments create a massive, chaotic wall of sound. That physical sound wave is captured by a microphone as a continuous signal, x of t, and then sampled 44,100 times a second to create a digital array, x of n. This diagram shows what happens next. The fast Fourier transform takes this digital array and separates the original signal into its component sine waves. This process reveals the individual frequencies and amplitudes that were mixed together, mapping them onto a frequency spectrum. This final cheat sheet groups these 15 symbols logically into 3 categories: canvas, anatomy, and digital. You can use these 7 golden rules to navigate the foundational vocabulary of any signal processing system.